In the last video, I said that we start off with, let's say we started off with the change in distance. So we said, that we know the change in distance. Change in distance. This is the things that we are given. We're given the acceleration. We're given the initial velocity. And I asked you, how do we figure out what the final velocity is? And in the last video, and if you don't remember, go watch that last video again, we derived the formula that Vf squared, the final velocity squared, is equal to the initial velocity squared plus 2 times the change in distance. You'll sometimes just see it written this as 2 times distance because we assume that the initial distance is at point 0, so that the change in distance would just be the final distance. But we could write it either way, and hopefully at this point you kind of see why I keep switching between change in distance and distance. Really just so you're comfortable and you see it either way. But what if this is for the situation when we didn't know what Vf is. But let's say we want to solve for time instead. Well, actually, once we solve for the final velocity, we can actually solve for time, and I'll show you how to do that. But let's say we didn't want to go through this step. How can we solve for time directly, given the change in distance, the acceleration, and the initial velocity? Well, let's go back once again to the most basic distance formula. Not the distance formula, how distance relates to velocity. So we know that, I'll write it slightly different this time, just so the change in distance over the change in time is equal to the average velocity. Right? Or we could have rewritten this as, we could rewrite this as the change in distance is equal to the average velocity times the change in time. Right? This is change in time, change in distance. And sometimes we'll just see this written as d equals, let me write this in a different color so we have some variety. Sometimes you'll see this is written as d equals velocity times time, or d equals rate times time. And the reason why I have change in distance here or change in time is, well, I'm not assuming necessarily that we're starting off at the point 0 or at time 0. But if we do, then it just turns out to kind of the final distance is equal to the average velocity times the final time. But let's stick to this. We want to figure out time given this set of inputs. So let's go back to, well, let's go back to this equation. Or actually, let's go from this equation. Right? So if we want to solve for time, or the change in time, we could say, we could just derive both sides, we could divide both sides by the average velocity. Actually, no, let's not do that. Let's just stay in terms of change in distance. So let me actually, I've wasted space too fast, so let me clear this and start again. So we're given change in distance, we're given initial velocity, that's initial velocity, and we're given acceleration, and we want to figure out what the time is. And if we assume, I mean, it's really the change in time, but let's just assume that we start time 0, so this is kind of the final time. So we know that, let's just start with the simple formula. Distance, or change in distance, I'll use them interchangeably. Distance, I'll use a lowercase d this time, is equal to the average velocity times time. And what's the average velocity? Well, that is just, the average velocity is just the initial velocity plus the final velocity over 2. And the only reason why we can do it, why we can just average the initial and the final, is because we're assuming constant acceleration. That's very important. But in most projectile problems, we do have constant acceleration downwards, and that's gravity. So we can do this. We can say that the average of the initial and the final velocity is the average velocity. And then we multiply that times time. And then, well, can we use this equation directly? Well, no. We know acceleration, but we don't know final velocity. So if we can write this final velocity in terms of the other things in this equation, then maybe we can solve for time. Well, let's try to do that. So, well, I switched colors kind of arbitrarily, but distance is equal to, well, let me take a little side here, because what do we know about final velocity? We know that the change in velocity is equal to acceleration times time. right? Assuming that time starts at t equals 0. And the change in velocity is the same thing as Vf minus Vi is equal to acceleration times time. And so we know the final velocity is equal to the initial velocity plus acceleration times time, right? So let's substitute that back into this, what I was writing right here. So we have distance is equal to the initial velocity plus the final velocity. So let's substitute this expression right here. The initial velocity plus, now the final velocity is the initial velocity plus acceleration times time. And then we divide all of that by 2 times time. And so we get d is equal to, so let's see, we have 2 in the numerator, we have 2 initial velocity, 2 VIs, plus AT over 2, all of that times t. And then we can simplify this. This equals d is equal to, let's see, this 2 cancel out this 2, so we have, and then we multiply, we distribute this t across both terms. So d is equal to VI t plus, and then this term is AT over 2, but then you multiply the t times here too, so it's AT squared over 2 plus AT squared over 2. So there, we could use this formula if we know the change in distance, or the distance. We could say, we could say this is the same thing as the change in distance. This actually should be the change in distance, and the change in time is equal to the initial velocity times time plus acceleration time squared divided by 2. So let me summarize kind of all of the equations we have, because we really now have in our arsenal every equation that you really need to solve a one-dimensional projectile problem. Things going either just left, right, east, west, or north, south, and not both. And we'll do that in the next video. But let's summarize everything we know. Image. So we know the change in distance divided by the change in time is equal to velocity, average velocity. It would equal velocity if velocity is not changing, but average when velocity does change. And we have constant acceleration. That's an important assumption. We know that the change in velocity divided by the change in time is equal to acceleration. We know the average velocity is equal to the final velocity plus the initial velocity over 2. And this assumes acceleration is constant. Acceleration constant. If we know the initial velocity, the acceleration, and the distance, and we want to figure out the final velocity, we could use this formula. Vf squared equals Vi squared plus 2a times really the change in distance. I'm going to write the change in distance because that sometimes matters when we're dealing with the direction, times change in distance, but you'll sometimes just written this as distance. And then we just did the equation. I think I did this in the third video as well early on. But we also learned that distance is equal to the initial velocity times time plus AT squared over 2. So in that example that I did a couple of videos ago where we had a cliff, actually I only have a minute left in this video, so I'm going to do that in the next presentation. I'll see you soon.